So, hello and welcome to this fifth lecture in the DP Roy Memorial Lecture Series. As you know, this is in the memory of our colleague, Professor DP Roy, who has been associated with TIFR for almost 5 decades and perhaps even more. Uh, Please make sure that your mobiles are on silent mode. And to start our proceedings, let me invite our director, Professor Jairam Chenglur, today's speaker, Professor Michelangelo Mangano, and Mrs. Roy on stage. Please. Thank you. Uh, it's a pleasure to have Professor Michelangelo Mangano here from CERN, who has been working for more than 5 decades, if I'm correct, in the areas very, very similar to the areas that Professor Roy has been working in. And let me request our director to welcome him with a bouquet and a gift. Let me now request our director to say a few words of welcome and about Professor Roy.
Good evening and welcome to TIFR. We are here today, as we just heard, for the DP Roy Memorial Lecture. And again, as we just heard, Professor DP Roy was a very well-known member of the TIFR physics community. He had a very long and distinguished career at TIFR at Colaba, starting in 1976 until his retirement in 2006. However, even after he retired, his association with the Institute continued. He was associated with HPCSC, first as a Raja Ramana Fellow, and then as an INSA senior scientist. And so he continued to be very active in physics until he passed away in 2017. Professor Roy was very well known for his contributions to collider and neutrino physics, and was the recipient of many accolades, including the Meghnad Saha Award and the S.N. Bose Medal. So this particular lecture series, the DP Roy Memorial Lecture Series, organized in his memory, is enabled by a very, very generous donation from his wife, Dr. Manika Roy. And we're very fortunate to have Dr. Roy with us today. And I would like to thank her again for her very generous and thoughtful contribution. Donations such as these are critically important to enable activities at TIFR, which play a very central role in building up the culture and ethos of this institute, and which are very difficult to fund through our normal funding channels. The lecture series that we have, the DP Roy lecture series, typically consists of a public lecture and 1 or 2 technical talks. And this is the 5th, as we just heard, DP Roy Memorial Public Lecture. And it continues the tradition of bringing scientists of very high eminence to TIFR. This year, we are delighted to be hosting Professor Michelangelo Mangano, from CERN, Switzerland. We will have a more formal introduction of the speaker shortly, but right now I'd like to take the opportunity to thank Professor Mangano for accepting our invitation and spending time here at TIFR. There was a more technical talk by Professor Mangano yesterday, and today we have this public lecture in a more sort of general topic. TIFR has had a long tradition of having such public talks as a way of communicating cutting-edge scientific research to the general public. These are well advertised on our social media channels, so please do follow them. Today's talk also actually connects with another very long-standing tradition of TIFR, dating all the way from our founder, Dr. Homi Bhabha, of staying connected not just with science, but also with the fine arts. So it's a special delight to have this lecture by Professor Mangano, and I'm very much looking forward to what he has to say. Thank you, and welcome again.
Thank you, Professor Shenglur. Before proceeding further, let me just mention a few things about Professor Roy. One is, of course, that he got his PhD from TIFR. So he was a student of Dr. Udgaonkar long ago. And his contributions that remain in people's minds even till now, one was on his exploration of charged Higgs and looking at the signals at the colliders. And the second was in the area of neutrino physics. So in fact, when the first results on solar neutrinos came out from the reactors, his group was one of the first to actually figure out, zoom in on the exact parameter space of oscillations of solar neutrinos. So I think these two contributions will actually be remembered for a very long time. Let me now request Mrs. Roy to say a few words. Maybe we can take a mic to her. You want to come in? It's fine, Jimmy.
Good evening. This is, I am very happy to come to TIFR for my memorial lecture of Professor D.P. Roy. I am grateful to the D.P. Roy Memorial Committee members for arranging this beautiful lecture series. This is the 5th in the series, and this was started in the year 2018, 1 year after the death of Professor D.P. Roy. And actually, I wanted to do something, but it was the suggestion of the theory group people that the lecture was initiated. And they have taken a lot of care and a lot of efforts to keep it alive. And every year they are improvising. And I am really grateful to them. And I hope this will continue. Same efforts will continue. And this was done in a line of thought of Professor D.P. Roy, because she used to like conference interaction with students and get together where the ideas spring up and they have collaboration work. With this view in mind, he started WEP along with Professor Prof. Roy, and from which lot of people are benefited in the research field. He was also interested in undergraduate teaching, and for which I think with Professor Chitre, they have started a course for undergraduate or postgraduate student at Kalina campus, Bombay University, which is also doing a lot of good job. He was actually an educationist in his life. In his choice of subject, his teachers played a very important role. Soon he was born in a village called Mahanga, which was about 26 kilometers from Cuttack, Odisha. His father was a freedom fighter and very strict disciplinarian. He arranged very good teachers for his children's education. And when he went to the village school, and there it was a surprise that he was promoted, double promotion. In those British India, there were double promotion. He was promoted from fourth to sixth. Then he went to a school which was very far from his house, inside the alleys, paddy field, which is very slippery during the rainy season. And there, the school was essentially a primary school with 7th standard. As they passed and go to one class in the summer, they used to help the teacher to build the classroom. So classroom was built, teacher will be instructed from down, and the children will be up with putting knot in the bamboo. These are the classroom with thatched roof. This is how education began. And he was influenced very much by his teacher. He was a very good teacher, and science teacher was very excellent. That is the reason he came to science. Then he came to Ravenshaw College for his BSc and MSc. There also, he was very much appreciated. That is, I heard from him and from his friends, classmates, if the children have any difficulties, they don't go to their teacher. They used to come to DP for solving the problem. And then he went to Delhi University, and after that he came to TIFR to do his PhD. After finishing PhD, he went abroad for 10 years, even came to TIFR in 76. And we stayed here in TIFR colony more than 30 years and immensely benefited by our stay. Still very nostalgic feeling. Whenever I get an opportunity to come to TIFR, I come. And this is a small tribute in respect of Professor D.P. Roy and also our stay in TIFR, which is fruitful in many ways. That memorial lecture was launched with the help of his colleague and students and the director of TIFR. That time Professor Sandeep Trivedi was the director. He is also physics group, theoretical physics group. That is how we started. Subsequent directors also supported this thing. Professor Ramakrishnan and then Professor Singalur. With their constant encouragement and effort, this lecture is going on. And I hope it will go on when I am not there, and they will try to make it successful and useful for the students and teacher community. And any help you need from our side, we are prepared to do. Secondly, I want to thank our visitors, Professor Michelangelo Mangano. I'm sorry, I could not pronounce it. In spite of his very busy schedules, he made a time to come here and give this lecture series. And today's public lecture is one will be very interesting, and we are looking forward to it and enjoy it. I am sure all levels of students and teachers will enjoy and benefit from this lecture. Thank you very much, sir. With this, I don't have to say anything. Only thing I would like to thank all the people who are present today here and those who are present in the website, in the Zoom, and also YouTube, and thank them and hope they will enjoy the lecture. That's all. Thank you.
So thank you, Manikadi. Now I would like to request Professor Manoranjan Guchait to introduce today's speaker. Manoranjan.
Thank you, Amal, for giving me this chance to introduce Professor Michelangelo Mangano, whom I really try follow the way he does the physics, that is a data-driven physics. Michelangelo Mangano, in the community popularly known as either MLM or the Mangano. And he is known to us, at least I know him since he came in Calcutta. That time I was a student. We had a workshop and he was attending along with Hitoshi Murayama and others. And I remember in Top Course Physics, to understand some events, he taught me how to really look at the problem and analyze it. Anyway, and Professor D.P. Roy, Professor D.P. Roy was also a very good friend of him. Mangano graduated in theoretical physics at the Scuola Normale Superiore, Pisa, Italy. He held research positions at the physics department of Princeton University in the theory group of Fermi National Accelerator Laboratory, USA. He was associated with the Italian National Institute of Nuclear Physics. Since 1995, he is senior scientist in the theory department of CERN, where his research focuses on the properties of high energy physics, particle collisions, and their relevance for the exploration of fundamental interactions. Between 1988 and 2000, Mangano has also collaborated with the CDF experiment at the Tevatron Accelerator, contributing to the discovery of the top quark. He has immense contribution in the QCD, which is the driving force for the Hadron Colliders. He and his collaborators have studied several important processes in the Standard Model, and few of those, namely the vector boson production, vector boson plus jets, TT bar production plus jets, and so on. So based on their calculation, they developed a tool which is very user-friendly code, that is we call AlpChain. During my student days, I used AlpChain. This is it gives the cross-section of various kind of standard model particle productions at the Hadron Collider. And his prescription also for the jet quark matching for the hadronic simulation is also very useful and important. It is being used widely in all experiments, collaboration, and also in the theory. Mangano leads the LHC Physics Center at CERN, which contributes to the activities of interpretation of the LHC data and coordinates the exploration of the physics potential of a 100 TeV proton collider in the context of CERN's studies for a future circular collider. Right now, the worry in this field is that we are really at the junction of a crossroad. From here, we do not know where to go. We have established the standard model, and after the standard model, what next? And several of us in the community, we believe there is an extension of the standard model. Of course, there are sufficient experimental and theoretical reasons why do we believe the standard model. And then the question is, what kind of extension we have? Several proposals are there, but which one is correct? So far, the data didn't confirm anything. And what the current experiment is going on, either at the LHC, high luminosity LHC, or the KEK laboratory and others. So far we have not seen any evidence. Then after that, what? If we don't see any evidence, should we stop it here, or we'll go for the next generation of collider? Now, if we go for the next generation of collider, then the question is, what kind of collider? Is it a linear collider, or is it a circular collider? Is it a lepton collider? Is it a hadron collider, or is it a lepton hadron collider? All sorts of options are there. And at this stage, here, Mangano plays a big role. Okay? So huge activities and discussion are going on in this direction, and Mangano is engaged very actively and play a very crucial role at the highest international level. He is one of the very important and key member of the committee working on to propose the strategies for the future direction of high energy physics, in particular the experimental physics. Yesterday, he delivered a very thoughtful talk in DTP colloquium, explaining various aspects which are being considered to decide our next generation of high energy physics experiments. Today, now we'll listen more on that. Beyond his research, Mangano is equally involved in scientific outreach. He created and directed in the period of 1990 to 2005 CERN's High School Teachers Program, a summer stage for physics teacher. Since 1998, the program has been followed by over 6,000 teachers from over 70 countries worldwide. Better now I stop here and listen from him. Thank you very much.
Thank you, Manoranjan. Let's now hear the talk of Professor Mangano. I would request Professor Chengalur and Manikadi to come downstairs.
Well, thank you, everybody. Thank you, Manoranjan, for this flattering introduction. Thank you to Dr. Roy, and thank you to the director for the invitation and the opportunity to be here once more in this auditorium and sharing some thoughts on, in fact, a topic which is not directly focused on research, but that tries to put what we do under a different perspective, which is VR perspective. And as you all know, and as has been mentioned, this also resonates with the culture of TIFR, where we can look at all of these paintings distributed through the facility. Oh, yes, I have this. That's right. But before I get into that, let me just say a few words on, we need to move also this one to the side. Few words on the relation with Professor Roy, with the DP. It's a relation with CERN, which is my home institution, and it's a personal relation with me. And as I say here, it is a story of friendship. DP was a postdoc at CERN in the late 60s. He was on sabbatical in 91, and then in the course of the years, he paid short visits rather frequently in all of those years. And those were occasions, of course, for us to foster our own personal relations. I think that I first met DP, in fact, even before that, it was in the late 80s in the US during some of the several meetings and workshops that we were having. These are just a couple of papers from 94 and one from 99, which emerged from his visits, his relations with CERN, and in fact, his relations with me, because I can find my name in the acknowledgements at the end of these of those papers. So this really proves that I've been a close colleague of his since back 30 years. There is another reason why it's not unreasonable to combine the concept of invisible to DP, because DP was also interested in the invisible aspects of our universe. And in fact, there are at least 6 papers that have the word invisible directly in their title. For example, signatures of invisibly decaying Higgs particles, a general overview of the topic, basic constituents of the visible and invisible matter, a microscopic view of the universe. So clearly, this indicates that it's not unreasonable to discuss invisible in the context of a presentation about science. Invisible always comes with this connotation of esoteric, exotic, mystic, while invisible, as I will try to convince you in this presentation, is something extremely concrete, to the point that what is invisible is really the starting point of scientific exploration and progress. I highlighted here, in addition to the word invisible, I highlighted names, I highlighted CERN and institutions which somehow reflect once again the multitude of connections and relations that DP had in general with the community, with labs around the world. And I have to say that several of the people in these slides, some of them are even sitting here, Mono Ranjan, for example, are my own colleagues and friends, and I developed friendship with Indian physicists and with TIFR, also thanks to DP, and this I'm certainly very grateful for. So let me now come to this image with which I opened my presentation. This is a picture of Salvador Dali, and artwork by Salvador Dali will accompany this presentation, will provide sort of an underlying theme. And the reason is that Salvador Dali had, some passion for science and for physics in general. And I think that no artist better than Salvador Dali, in fact, represents the inspiring power of science and has been more fascinated specifically by the relation between visible and invisible. He wrote in this document, which is called the Antimatter Manifesto, in the Surrealist period, I wanted to create the iconography of the interior world and the world of the marvelous of my father, Freud, so psychoanalysis. Today, the exterior world and that of physics has transcended the one of psychology. It's an incredibly powerful statement. My father today is Dr. Heisenberg. Heisenberg is one of the fathers of quantum mechanics. This is a picture of a cluster of galaxies, the Abel cluster. Looking at the sky has been inspiration for both scientists and artists throughout history, since the very beginning of civilization. He was looking at the stars with the first theoretical ideas about how the world works came up, understanding the motions of the planets, of the stars, the phenomenon of the sun, the moon. All of this has always been one of the things that we observed in nature, and even though it was not palpable, it was not, we couldn't directly connect to that, we couldn't touch it, but provided inspiration. In addition, the vision of a night sky is one of the most amazing views that we can have on our universe. So it's not unreasonable that somebody like Dali, this doesn't really work very well, was inspired by, I really think I prefer to use my keys. One of the things that he painted was indeed skies in Dali's style. He said, if physicists produce antimatter, let the painters, who are already specialists in angels, paint it. Of course, if he had access to the skies that we can see today through our telescopes, who knows, how more magnificent his representations of the mysteries of the skies would be. One reason why I start from this image of the skies is that, in fact, however beautiful and fantastic this picture is, what is really interesting in it is not what we see, but is what we don't see at all. And we know that there is something in that picture that we cannot see and doesn't display in the picture because of the following. This process is called this mechanism is called gravitational lensing. Let us suppose that we are sitting on Earth. Let's see if this works. Yes, down here. And very far away, there is a galaxy at the edge of the universe. And the light from that galaxy to reach us has to go through a cluster of galaxies like the one we saw in the previous picture. Now, there is a fundamental result in Einstein's theory of gravity, that gravity will bend light. It will really work like a lens. And this means that the light emitted this way from that galaxy will be bent and will reach us, and likewise there will be light going this way that comes to us. So this cluster of galaxies in between really acts as a lens. And a lens, a generic lens, is going to distort the image. In fact, when we buy glasses, we really need a professional who makes them so that at the end, our eyes can focus and improve the vision. Otherwise, it gets all distorted. If we look at the light coming from these faraway galaxies through a galaxy cluster, we see that indeed there are indications of distorted images. These are the galaxies which are cleanly defined in the cluster between us and this more remote system. And then there are these highly distorted as you see, and bent images, which really correspond to galaxies sitting beyond. Now, as in the case of a lens, we can calculate as a function of, how thick is the lens, what is the material of the lens, etc., we can calculate the properties of deformation of the light. In this way, we can calculate how much matter there has to be in this cluster so as to induce such a gigantic deformations of a point-like image that's sitting far away. And the conclusion of this calculation is that the visible matter that we see here in this cluster is by no means sufficient to induce these deformations. There has to be much more material in the cluster to justify this. But that we don't see. So the conclusion is that within a cluster of galaxies, and in fact, through other measurements, the conclusion holds throughout the universe, there is much more matter than we can possibly see. And this gives origin to this concept of invisible dark matter, whose origin and whose consistency is one of the big mysteries of science nowadays. So what is the bottom line of this? For the purposes of the presentation, the idea that for something to be declared invisible, we must know it's there. Invisible is an adjective, which means something is invisible. It's not an abstract concept, it's very concrete. So if something is, in order to make a claim about something that you cannot see, you must know that there is something. Otherwise, you wouldn't even know, and you wouldn't say that this is invisible. I am not saying that there is an invisible dog in this room, because I have no indication that there is a dog. If I heard barking here on stage, I would say there is an invisible dog. If I don't hear barking, I don't know. Maybe there is, but nobody would know. So it's crucial to know that something is there. And if we know that it's there, then, even the word invisible is not appropriate, because we know it's there. Whether we see it or not doesn't really make a difference. If we think of people who are blind, for them, in fact, the difference between visible and invisible is very artificial, because they don't use vision as a way to recognize the presence of objects. Now, and I thought I had, yes, so this is one example, and this is one of these ways in which Dali connected the science and this concept of invisible with the art. There is this painting which is called the Surrealist Composition with Invisible Figures. Now, it's clear that there are invisible figures here, because we see it in the bed and in this chair. There are shapes, so somebody is actually lying there, even though we don't see it. So these are invisible figures. Okay, so we know it's there, we don't see it. So proving the existence of invisible, namely providing evidence that there is something where there appears to be nothing, turning the invisible into visible, is in fact, turns out to be one of the main drivers of scientific progress. If you think about that, it's a very basic process. It's something that takes us from the realm of magic and superstition to the domain of science. Think about medicine. people used to fall ill and nobody knew what it was. Think about the Black Plague in Europe, for example, during the Middle Age. Then they had no idea what it was. It was invisible. And it's discovering exactly what it was that made it possible for science to make progress and eventually to cure the disease. Before, it was just, some god being upset with us. Or think about, storms and all of the natural disasters. So really understanding the invisible and turning it into visible, something that we understand really is even philosophically a transition from magic and superstition to science. Now, this is another picture of Dali called Invisible Harp. Here, contrary to the previous one, it's not obvious that there is something invisible. I mean, we don't really see the trace of something missing. And even if we did, why should it be a harp? Before, we had the shapes of the bodies. Now, what is it that is invisible? Why should it be a harp? So this is the second part of the story, and in fact, it's even more important, which is that establishing the nature of invisible is a really crucial step. Step number one is to recognize that something is invisible, but then we need to understand what this invisible is. Think about, the planetary system, the solar system. We don't see strings attached between the Earth and the Moon, the Earth and the Sun, and the planets. We just see them going around. And what is the force that keeps us all bound together? What is the force that keeps us bound to the Earth? It's invisible because we don't see it. I can walk on a tree and there is nothing that is actually keeping me tied to the ground. So what is the origin of these invisible forces that tie things together? Once upon a time, they thought, you may remember, there were the celestial spheres, so planets and stars were actually, attached to physical spheres that were surrounding the Earth and on which things were moving. Now we know that certainly that is not the case. More in general, what is hidden inside things and what are things ultimately made of? If we start cutting the usual exercise of cutting, where do we get? Do we get to something which is a fundamental element and component? So the goal of modern physics is, number one, unveil the existence of some invisible, but then to give it substance and also explore the consequences on the universe. So there are a couple of questions right away fundamental that we can ask, which is, are there fundamental building blocks? The exercise of cutting up, do we end up with something out of which we can build everything we see, or are we going infinity to keep cutting and cutting and cutting? Is there a fundamental building block of matter? If so, what are they? How do they interact? What is it that keeps them together? What are the laws of nature? And in fact, how do they determine the properties of the universe? So in the course of the past, whatever, depending on how you count them, it's 180, 60, 50 years, we did develop an understanding and an answer to these questions. And today we have the so-called standard model of particle physics. We take matter. Matter is made of atoms. Atoms include a nucleus and electrons going around. Inside the nucleus, we have neutrons and protons. And inside neutrons and protons, we have objects which we call quarks. And the electron and these quarks, for all we know, are fundamental and they are point-like. There is no way we can identify additional structure inside. We cannot keep cutting an electron over and over again. The electron is an electron is an electron. There is nothing inside, and it is a fundamental building block. This is what all of the experimental evidence tell us. In addition to the building blocks of the matter that we see around, there are two more families of building blocks which are very similar to the fundamental, to those we know, which tables are made. They have exactly the same properties, but they are much heavier and they are unstable. They do not live long, so they do not contribute to create a stable matter, but they are there. And the question of why are they there, what are they needed for, is one of the big questions. So this is the matter in the sense of the particles, the electron, the proton, the quarks. What are the forces? A priori, you know, once upon a time, it doesn't have to go very far back, but even a couple of 100 years ago, people thought that, you know, electricity and magnetism were completely different objects. The wind is a force because the wind pushes boats, sailboats. But, you know, is it a fundamental force? Where does this force come from? At the end of the day, what we've learned today is that there is only 4 fundamental forces. One, of course, is gravity. And then there is electromagnetism, which is a unique force that behaves in different ways depending on the circumstances. There is a force associated with interactions that lead to radioactivity. And in fact, this force itself is very closely connected with electromagnetism. And then there is a force that keeps quarks together inside the proton and the neutron, and proton and neutrons together inside the nuclei. So these 4 fundamental forces and the particles I mentioned before are enough to explain absolutely everything we see in the universe. There is an additional ingredient now, which is the famous Higgs boson, on which I will say something later on if I have time left. So the description of natural phenomena that come from these basic building blocks describes everything we measure in the laboratory. It doesn't describe dark matter, but everything that we can create and make on Earth is there. And the Standard Model in particular provides the underlying explanation of all of the nuclear, chemical, electrical phenomena, the atomic structure of the elements, electrical, mechanical, thermal behavior of metals, semiconductors, you name it. Okay, so we understand it all. And let me give you now a few anecdotes on how the history to get to this point somehow stumbled upon invisibles and how these invisibles led us to a better understanding of the universe itself. In fact, if one were to look at it, you know, piece by piece, it all starts from invisibles. And the first ingredient in these is neutrinos. Neutrino was mentioned before as being one of the pillars of the scientific career of DP. So again, it therefore makes sense for me to review, to include neutrinos in this presentation. In the late 20s, so 100 years ago, there was a puzzle. There was a nucleus, helium-6, known to decay to another nucleus, lithium-6, emitting an electron. So there is a transformation of this nucleus, and it was emitting an electron. How this was happening was not understood at the time. It was an observation. Now, the observation was also that if this is what really happens, using conservation of energy, we would conclude that the electron energy is fixed, and it's equal to the difference in mass between the helium and the lithium nucleus. So the electron should always come up with exactly the same energy. But this didn't seem to be the case. In some cases, the electron was coming out very slow. And in some cases, the electron was coming out very fast. So the energy, the bookkeeping of the energy doesn't hold. And for quite some time, the physicists were puzzled by this behavior. And in fact, they were thinking that maybe at the level of nuclear phenomena, energy conservation didn't hold. They were really facing many, many puzzles. I mean, physics in those days was very weird, and they were open to everything, including the possibility that energy not be conserved. Wolfgang Pauli, this physicist, actually had the vision that there was a very simple answer to this puzzle. And the answer was that in the process of a decay, there is something which is invisible and which produces energy, carries energy in the decay. So the real decay is not helium goes to lithium electron, but it's helium going to lithium electron and this object that was then called a neutrino by Enrico Fermi. And if that's the case, energy and neutrino, they share the energy. So there are cases in which they share the energy evenly, and there are cases in which the neutrino has little energy and the electron has a lot of energy. So this explains perfectly this puzzle. Neutrinos, however, were invisible. Couldn't see them. So it was an hypothesis. An hypothesis that, however, explained everything, this phenomenon and many others that were seen later, to the point that even though a single neutrino had never been materialized, still all physicists knew and accepted the idea that neutrinos existed. However, 20 years later, in fact, a bit more, using these invisible neutrinos coming from some decay and shooting them on a target, at some point something happened that was the indication that the neutrino was there. It was the creation of a muon. So there is a picture, an image that proves that a neutrino, in fact, has a physical existence. Simply, it's invisible. It's invisible because it doesn't emit light and it doesn't interact with matter at a large rate. Whoops. So this immediately, again, fascinated Dali, who in the same Antimatter Manifesto declared that it is with pi mesons, which are used to produce neutrinos, for example, and the most gelatinous and indeterminate neutrinos that I want to paint. It is with these that I want to paint the beauty of the angles and of reality. Dali was crazy, right? I mean, you realize already, if you don't know him, that he was completely nuts. He was putting together these words, these concepts, these ideas in this potpourri. Still, as an artist, he was okay. He was legitimate, and clearly he was very, very inspirational also for scientists, in a sense. So nowadays, we see neutrinos on a daily basis. You wouldn't see them at home. Each of us, every second, is passed through by thousands of neutrinos that are produced from cosmic rays. They come from the cosmos, they go through, they don't interact, and therefore we don't feel them, but it is happening. So what we need is huge amounts of matter for one neutrino to interact. And if you recognize here, it looks like it's a lake. It's actually a big cylinder underground. It's all surrounded by detectors. These are like little cameras that make pictures of light. This is filled with water. When the neutrino goes through, as I will show you, leads to an interaction. It creates something else that interacts, emits light, and then we know that the neutrino had passed. And neutrinos, as I said, they come from cosmic rays, so they are there. In principle, we don't even have to produce them. And when they interact with matter, they're moving at a very, very large speed, the products of a neutrino, and they generate this Cherenkov radiation. They create a sort of a sonic boom that manifests itself with this cone of radiation coming out of the interaction. And this is exactly what is observed. This is you see each of these little squares is one of those cameras that I was mentioning before. Here we are inside, you see the cylinder. This is the base of a cylinder. This is the height filled with water. And all of these green points are detectors that have been reached by a flash of light. And as you see, it does reconstruct this cone, which is the Cherenkov circle of the light. So this is the type of images with which today neutrinos manifest themselves. So they're not invisible any longer in the sense that we identified how to make them visible, how to see them. And one thing remarkable is that occasionally these neutrinos come from the sun, because the neutrino is a natural product. It's always present whenever energy is produced inside the sun. Neutrinos coming from the sun can be seen because with those detectors, you can actually point, you can reconstruct, depending on how this Cherenkov ring is oriented, you can tell where the neutrino is coming from. If you map where they're coming from, what you see that there is a cluster that is pointing exactly towards the center of the sun. Now, the center of the sun where the neutrinos come from, there is no way we can actually see, because we would have to go through the whole sun. There is a huge amount of noise. I mean, a photon, which is light produced at the center of the sun, takes millions of years to come out of the sun, because, you know, it's like a photon moving in water. It slows down, it keeps interacting. There is no way we can possibly see inside the core of the sun. We do it with neutrinos, because neutrinos, since they interact very, very lightly, they can, you know, go through the sun. They come to us. Occasionally, we don't see them all. We see one occasionally, but it's enough to get a picture of the core of the sun. So what is paradoxical here is that we're using something which is invisible to detect and study a part of the sun that we would never be able to look at using visible probes. You see the paradox somehow, but also the power of having this invisible object, the neutrino. So it's been 100 years since neutrinos were put forward, and now they are a key element in our understanding of nature. They are the most intriguing objects of a standard model. The reason why DP was working on neutrinos, was proposing experiments, etc., is because there are many open puzzles. What is the precise value of their masses? We cannot put them on a scale because, you know, they travel at practically the speed of light. We cannot stop them. We cannot really manipulate them. We can only see that there was one that passed through, but we can't stop it, right? Why is their mass so much smaller than all other standard model particles? They have a mass which is very, very small, very close to zero. Are neutrinos their own antiparticles? How many types of neutrinos there are? Some we know, but there could be others. Do they feel forces which are not necessarily those of a standard model? Maybe there are other forces that only the neutrinos feel. We don't know. So there are many questions about neutrinos, and this is why neutrino research is one of the pillars of our program. With quarks, we make protons and neutrons. And the question is, why don't we, you know, look at a quark? The neutrino is invisible. What about the quark? Can we see it or not? The quark has a charge, so it emits light. But you've never seen a picture of a quark. And the question is why? Well, it turns out that even more than neutrinos, quarks are in a sense invisible. And the reason is that they are forever confined within the proton, the neutron, or the pion. The pion is the equivalent of a proton, is made of a pair of quark and antiquark, and they are tightly bound inside. If we want to make the exercise of stripping apart the quark and the antiquark, we take them, we pull them one from the other, and by doing that, we generate potential energy, because there is a very, very strong force that keeps them together, and the force is constant. So the further away we go, the higher is the amount of energy that we must put into the system. But at some point, the amount of energy that we are giving to the system by separating quark and antiquark, this amount of energy is larger than the energy sufficient to create a quark-antiquark pair. E equals to mc squared. So as soon as the energy is larger than twice mc squared, where m is the mass of a quark, all of a sudden a quark-antiquark pair pops up. And then the quark goes the antiquark goes with the quark, and we end up with two pions. So we cannot take apart a pion into quark-antiquark. If we try, we end up with two pions. And this goes on forever and ever and ever. And we will never be able to do that. So in a sense, you know, quark is really the ultimate invisible. There is no way we can get them out. But again, we know they're there. And we know they're there because there is a series of measurements, indirect, if you wish, which give us absolute confidence that indeed they are there, because otherwise we wouldn't been able to explain everything else we see. So pions, which I just mentioned, were also a topic of production for Dali. He is a saint surrounded by 3 pi mesons. And it looks very much like, you know, the pions that come out of a physics collision. This is an event, a physics event, in which there is a beam coming out from there, there is an interaction, and all of these streams of particles coming out. So this is real, and this is Dali. And as you see, it's not... it's not too far from reality. His imagination was immense. So some of the main open questions dealing, as we will see also again, with invisibles. We already discussed the origin of, I already introduced the concept of dark matter. Understanding the origin of invisible dark matter is one of the open problems. There are hundreds of experiments all over the world that are trying to understand what dark matter is, either by capturing some dark matter in space, space is filled with dark matter, or producing, artificially creating particles which are dark matter. And the way we recognize it is that since dark matter is dark, if we were to produce it, we would see something that we don't see. In other words, we would see that energy went in, but energy didn't come out in a visible way. So it's very similar to the concept of a neutrino. We would see reactions in which energy conservation seems to be violated because something is taking away energy that we don't see. If we were to detect events like that, that would be an indication that we are in fact creating dark matter in the laboratory. And there are many experiments, as I said, that are trying to do that, even at CERN. Whatever happened to antimatter in the universe? Antimatter is, another of the big manias of Dali. He wrote this antimatter manifesto. He was fascinated by the concept of antimatter. At the beginning of the universe, there was as much matter as antimatter. When the universe was very hot, at some point it started cooling down, and for some reason, an imbalance between the two was created, and only of the order of, one particle of antimatter over 10 to the 10 of matter survived. So there was a mechanism during the beginning of the universe in which antimatter got annihilated with matter, and what was left was radiation plus just a few crumbles of matter. Those crumbles are what makes our universe today. Exactly what happened, how it happened, why did it happen, we don't know. That's one of the big questions, and that's one of the things that we are exploring. Why do we live in 4 dimensions? I say 4 because usually we think of 3 space dimensions plus time. So 3 plus 1 is 4, and that's where we live in. Seems like a stupid question. We live in 4 because we live in 4. Why do we ask? Well, the point is that even gravity is something that we have a theory for. And ideally, we would like to understand where does gravity come from, and not just Newton's law, F is equal to 1 over r squared, but something deeper. And general relativity by Einstein, in fact, provides us a much deeper view of what gravity is. Gravity is about the bending of space-time. So there is some mathematics, there is geometry, there are connections with deep theories, like, for example, string theory. And as we move into the realm of mathematical understanding of gravity, we realize that, in fact, 4 dimensions have nothing special. And in fact, say in string theory, we'd much rather be living in 10 dimensions. So are we sure that we are only living in 4 dimensions and not in 10? We don't see the 10, of course, but maybe those 6 are all curled up into something very small. We don't see them, but if we were to be able to go to very, very, very short distance, all of a sudden we would be seeing that there are other dimensions, which are, again, hidden from us. So the question is, are there hidden dimensions in our universe? It's a big question. Experiments looking at least for hidden dimensions at a scale which is experimentally accessible are taking place, but still the answer is we don't know. Now, I mentioned gravity, and gravity is the force that, most naturally everybody comes to grip with. Typically a baby who's born, hopefully he will never put his fingers into the electric plug, so he will not know about electromagnetism for a while, but certainly he knows about gravity because as soon as he tries to stand up and walk, he will fall down. So gravity is a trivial and obvious object, but it's actually something very deep that poses deep puzzles to scientists. And if I manage to get, so I have I hope it works. I do have a small video here which represents a small experiment that I've done, which I'm sure you have all done in your life. I hope everybody's familiar with this phenomenon, right? Again, you're so familiar, but you don't even think about that. But what is happening here is absolutely amazing. Why is that piece of paper lying on the table, on the desk? Because gravity pulls it down. Why is it now? Why can I lift it with that? Because I induced some electricity, some charge on my pencil. So the force, the electric force, is balancing the gravitational force and is pulling up that piece of paper. But that means that the few electrons that I was able to excite, if you wish, the few charges that I was able to excite, created an electric force which is as powerful as the gravitational force generated by the whole Earth. What keeps that piece of paper on the desk is the Earth. It takes something as big as the Earth to keep that thing down. And it's enough to go like this with my finger, and all of a sudden I've generated a force which is bigger because, in fact, I lift it. So that gives you a sense of how weak gravity is. Gravity is strong because if I fall from a tree, I kill myself. But it's the whole Earth. If there were me and someone else, we wouldn't be attracting each other. We are attracting each other through gravity, but the force is so little that we will never realize it. So if one puts these into numbers, what we find is that if we take two protons, the electric charge between them is 10 to the 36 times stronger than the gravitational force between them. So gravity is 10 to the 36 times weaker than electromagnetism. Now, how small is 10 to the minus 36, or how big is 10 to the 36? 10 to the 36 is the ratio between the weight of the Earth and the weight of a brain cell, which is 1 billionth of a gram, 10 billionth of a gram. Okay? So that's how weak gravity is compared to the electromagnetism. The other forces in nature, the weak force and the strong force, we call them weak and strong, which means that they are weaker or stronger. Well, yeah, they are weak or strong with respect to the magnetism, but by a factor of 10. So pretty much doesn't change. Instead of having 10 to the minus 36, we will be 10 to the minus 35, 10 to the minus 37. So we have three fundamental forces which pretty much have the same strength. And then all of a sudden we have gravity, which is, a billion of times smaller. It's absolutely crazy. And it's something that, make us think. So why is gravity so weak? That is the question. And we have no clue. Is it anthropic? What does it mean? It's clear that if gravity were as strong as electromagnetism, we would all get squeezed, right? The Earth itself couldn't sustain itself. We just crash down to a point. The whole universe would be a point. You wouldn't be able to create structure. So if we're here, unavoidably, gravity must be much, much, much weaker. So there could be an anthropic reason. In that case, it would be a random choice of nature, and we're lucky that we got into it. It could be the outcome of some unknowing underlying dynamics, for example, extra dimensions. There could be a reason why this is true, because in worlds in which we have extra dimensions, the gravity we see could be so much weaker than weak interactions. And the question also is whether it's gravity that's very weak or maybe elementary particles that are unnaturally light. So at the end of the day, the question that arises from here is what is the origin of particles' masses? Because it's particle masses that react to gravity, okay? So, and this opens another question, which is why do particles have a mass? And this question for us is connected with the question of what is the structure of a vacuum that leads to the Higgs field. You have to tell me also how much time I have, because we started quite late. I didn't. Yeah, so I think I have another 10 minutes, right? Okay, that should be okay. So the question of void of the vacuum, is also something that Dali pulled out in this the echo void painting. The vacuum, what we call the vacuum, we call vacuum the state of any volume of the universe once we take away everything from it, matter, interactions, anything else. That's what we call vacuum. So we take this room, we empty it of chairs, of people, of air, etc., etc. It's not really vacuum because there is gravity, there is a gravitational force. If we go far away, distance from everything, we can have real vacuum. And the question is, can we really take everything out? Is there something left once we take everything out? So the standard model, in fact, predicts that the vacuum is occupied. You cannot really empty entirely a volume of space because there is something called the field of the Higgs boson. And it permeates the universe ever since 10 to the minus 10 seconds after the Big Bang. And the interaction with this field is what gives particles their mass. Now, one way to understand this is to look at what happens when light goes through a medium. As you know, light going through a medium slows down. That's why we have refraction. That's why the lens works. That's why when you look at a stick going underwater, you see the stick going like that. It's not that light goes slower in the medium, it's that when a photon enters into the medium, it starts interacting with it. So it gets absorbed by an atom, and then it gets re-emitted, travels at the speed of light until it's absorbed again, and then it's re-emitted, and this process slows things down. So you see here, it comes in, it interacts, then it's re-emitted, it moves. So this negotiation of moving through the medium is what leads to the slowdown, the effective slowdown of the speed of light, and the speed of light in the vacuum is smaller. Now, this Higgs vacuum does something similar, which is not a slowing down of anything. So it's not like mud. If you run into mud, then you slow down and you stop. It just leading this interaction with the medium leads to what we call inertia. So it's to create something to come to reality being produced has to interact with this Higgs that is surrounding the universe, and it has to pay a penalty. It's like a tax. It's a tax to come to life for a particle that has a parameter which we call mass, and which ends up being the physical mass, the weight of the object. The way we describe this is with that line where there is a particle moving and it keeps interacting with the underlying Higgs vacuum. How much Higgs vacuum there is depends, will define how heavy particles are. If there is more vacuum, of course, particles will be heavier. There is a fixed value, which in our notation is 240 GeV, whatever that means. We have a number, so we can define quantitatively what is the density of this object. So at the end, the question of why is gravity so weak can be turned into a question of why is the Higgs field so weak? Because if the Higgs field were much stronger, the masses would be much bigger, and then they would end up being comparable, the gravitational mass, to the electric forces. So what we want to understand is why is the Higgs field so weak, and to do that, we need to study the Higgs field. And to study the Higgs field, we have to produce it. And how do we produce it? Well, if we have something which is permeated by a medium, we can excite waves. This table is a medium because it's made of wood, it's made of whatever. It's silent, it doesn't emit anything. But if I go there and I beat on it, I create waves, and those I can hear. So I can do the same. I can take the Higgs vacuum and I can perturb it and disturb it so as to create a wave. And that wave, what we would call, well, first of all, it's a physical manifestation, like the sound that comes out of here. So if I can do that with vacuum and I create this excitation, that excitation can prove to me that in fact the Higgs is there. I have to tune exactly the frequency of this excitation, and this is what is done at the LHC and in the big experiments that we're making today. We really inject enough energy in a small volume to excite these vibrations, and this is what the Higgs boson that you probably heard about is about. And then once we created this wave, we can then study its consequences, its decays, how it behaves, and so forth and so on. And for that, we use accelerators, detectors, technology, and suddenly we do see signals. If you see these spikes, these correspond, if you wish, to the frequency of this excitation. We've been able to excite the vacuum at the precise frequency that would give evidence, which is this resonance is evidence that we are exciting the vacuum at the right frequency for having produced a Higgs boson. So there are many open mysteries. In general, we can classify them in different ways. Some, they emerge from experimental facts, the existence of dark matter, the asymmetry between matter and antimatter, neutrino masses. These are experimental facts which we don't understand and we'd like to explain. There are things which are in the standard model that we take as given, but it would be nice to understand where they come from. Why is gravity so weak? I just gave an example. So we keep testing also some of the bases of a theoretical, of a standard model. For example, quarks and electrons are point-like, I said. This is true up to the quality of the measurements. Maybe if we were to go deeper inside, we would find that even quarks and electrons have a structure. So we keep testing that. Are there additional forces and interactions? I said we have 4, gravity and the 3 others. Maybe there is other forces which are very, very weak and we haven't seen. Maybe there are forces that only act on dark matter. Dark matter, we don't see it, but maybe it has its own set of forces and there could be a universe, with planetary systems and everything, which is just controlled and governed by dark matter. We don't know, but it's a possibility, and in principle, it's a possibility that we can test with our experiments, etc., etc. Are there additional space-like dimensions? I already mentioned this issue. So what will be the next big discovery? It could be a new set of particles. As I said, we are looking at the particle responsible for dark matter. We may find it. There are particles predicted by this object, which is called supersymmetry or superstring theory. Maybe those could be the next discovery. It could be a new interaction, maybe a new very weak force. It could be a new layer of substructure inside what we consider as elementary, like quarks and electrons. Maybe we discover one day that indeed electrons do have substructure. Or maybe it's a new conceptual paradigm. For example, when the discovery that the speed of light is constant was not the discovery of a new particle or of a new force, it was the discovery of a fundamental fact about nature, that energy levels in atoms and nuclei and everywhere are quantized, again, is a fact of nature. It's not a new particle, it's not a new interaction, it's one of the fundamental behavioral rules of the universe. And it could be that the next discovery will be something along those lines. And God knows what, this will inspire artists like Dali to produce. Final remarks. The depth of our understanding of nature has reached new levels, uncovering the existence, the origin, and the role of many invisibles. Sorry, because I have another one. Final remarks. Let me go through this because it looks nice. This is another picture by Salvador Dali. So the depth of our understanding of nature has reached new levels, uncovering the existence, the origin, and the role of many invisibles. And progress continues on the remaining ones, the remaining invisibles, and the remaining open questions. However, the question is, are we ever going to end? Are we ever going to get to the end of the story? And we need to understand, however, that there will always be a new layer of unknown invisible. And that is what I call the invisible hand of nature, that decided that after all, there should be something instead of nothing. And that whether, why is there something instead of nothing, will remain forever a big question. To conclude, my deepest thanks to Dr. Manika Roy and to the Roy family for the opportunity to return to TIFR and be able to offer this tribute to the memory of my dear friend, DP. Thank you.
Thank you, Michelangelo, for this fascinating talk. Time for questions. Anyone? Yeah.
Thanks for the talk. It was wonderful. And my question is, would you place Dali in the same league as Escher?
How can I judge, right? How can I judge? The one reason why I'm involved with Dali is simply that one day I was invited by the Dali Foundation in Spain to a series of workshop conferences. There was like a 3-day, one day Madrid, one day Barcelona, one day there, in which they wanted to explore the issue of invisible in science with Dali. What they really wanted to know is whether Dali was actually a scientist, whether he had understood what he was talking about, and whether there were scientific developments coming out of his insight. So I was happy to participate. I studied, I learned. That's how I focused on him. I think it is a fascinating element, and the pictures are fantastic. He's certainly not the only one in art who have handled and discussed the issue of invisible. Escher has his own. In fact, in Escher, everything is visible, but it's perversely contorted. It's visible, but it doesn't make sense, right? So it is a new way, and certainly it would be interesting to embed that into a similar presentation, trying to look at the development of science from Escher's perspective, from the perspective of Escher's creation.
Yeah, I think his was more about infinity, isn't it? Representing infinity. Yeah,
Recurrency and never-ending. Yeah, in that sense, yes, absolutely.
And I'm sorry, the final question for me is that, is there still some hope to, stumble on supersymmetry at the current energy levels at CERN?
In principle, it is. We're not going to change much the energy. We're going to get many more data in the next 15, 20 years. And if indeed the supersymmetry we haven't seen because it's hiding very well, extra data may help. But it's more likely now that supersymmetry is really sitting at a higher scale, or that indeed the most elementary manifestations of supersymmetry, the minimal supersymmetric standard model, etc., are too naive, and there are additional ingredients in supersymmetry that make it more vicious to pull out. I'm a firm believer in supersymmetry, so I won't give up until the end.
Thank you.
And so was DP, right?
Any more questions? Yeah.
Hey, when you are comparing gravitational force versus electromagnetic force, what unit mass or unit charge you are taking into account? Because as you take higher mass, the force will increase. So how you are comparing, it is 10 to the power minus 36.
Yeah, that is taking the proton mass and the proton charge. If you were to take the electron mass and the electron charge, it would be even smaller, of course. But this is because the electron is lighter.
Yeah, why we choose to compare with these units?
Because the proton is a rather fundamental object. I can take a stone, but a stone is not a fundamental particle. We're not building the understanding of nature we're building our understanding of nature starting from the fundamental object. So the natural scale is the masses of a fundamental particle. the quark. And this is why, but the battery is probably. I don't think you need to get into detailed understanding of a choice of units. I gave you an example. You take a piece of paper and you can lift it. It takes the whole earth to balance that. What more do you want? Whether it's 10 to the minus 36 or 10 to the minus 32 doesn't really make a big difference. The point is that gravity is much, 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 much weaker than any other force we know.
Hi, Professor. That was really an enlightening talk. I think that encapsulates the spirit of TIFR. So my question is, so in your final remarks, you mentioned that the final point was about paradigm shift, right? So have you encountered similar paradigm shifts in art, which encapsulates science and transforms this into such things?
That's a beautiful question, which I'm not really qualified to answer, even though we can certainly make reference to Picasso. There have been paradigm shifts in that sense in art. I mean, you look at modern art and you compare it against Giotto, Michelangelo, and whatever. Clearly, there has been a sequence of big earthquakes and seismic revolutions. The same is true in music. And the same is true in music, right? I mean, dodecaphony and the transition from classical music in the sense of the 19th century to what we started hearing, passing through Alban Berg and everybody. So it was a smooth transition, perhaps, but we've seen it. What is interesting, perhaps, to remark is that there is a coincidence between these shifts in the world of arts, whether it's visual arts or music, at the same time in which these big paradigm shifts took place in science. And one can even argue, and even, on the different front, the front of, we started by discussing Freud. So psychoanalysis, that is also a manifestation of a different way of looking at the world. When Einstein comes and says that, time is relative, or, the speed of light is constant, and all of a sudden there is quantum mechanics, you cannot decide what something will be doing, you cannot control something because there is only probabilities. You put these in the hands, in the head of a philosopher, of a painter, of a musician, and of course that will lead to a paradigm shift. The details you can look up on initiative.
Hi, Michelangelo. Lovely talk and quite interesting also to learn how to give such talks, I think. I had a general question in the following way. Often you see people use these scientific terms as metaphor. And in art, of course, you showed that it leads to beautiful pictures, but it also leads to a lot of pseudoscience, where people use things like quantum to sell whatever they want to sell. So how do you think scientists should be dealing with things like this?
Gosh. I am deeply concerned about language in a broad sense. And I have to say that my criticism doesn't start from the abuse of scientific language that's done by the outside world. Rather, our lack of understanding as scientists of what the words we use are read and are interpreted by the public. Very often I say, if you go to, the experts in outreach, they tell you, you cannot use jargon. You cannot use complicated words. You have to use simple words. That's not something that I subscribe to. The main point is that if I use jargon, if all of a sudden I use a word that nobody understands what it means, somebody will stand up and will ask him, what does that mean? and I have the opportunity to explain. If I use layman speech, people will think that they understand what I'm saying, but actually they're not, because very often we use normal words. I give you an example, if I can. I have many, but one is really perfect. It's a story that has been told to me of one of a colleague, talking to one of these people who help cabinet members in the US develop, they have to go to a committee about science, and they talk to, they have somebody, who talk. And he was convincing him that, basic science is very important and basic science has to be supported. I think everybody in this room would agree. The congressman didn't accept that. And he said, no, why should we support basic science? He said, I don't want to support basic science. I want to support advanced science. Basic science is what you learn in elementary school, what's there to be supported. You see? So that is the prototype of misunderstanding. I was mentioning another one yesterday during my colloquium on the use of model versus theory. We as scientists believe a theory is more fundamental than a model, because a model is a model. If you go even to the Britannica Encyclopedia, theory is something, vague. You believe that you understand, blah, blah, blah. But you say, this is your theory. My theory is better. Yeah, this is true in theory, but in practice. So theory is something decoupled from the real world. While model is something that is used to describe and predict behaviors. And that's what we do. We build models of nature, even though we don't like that word, because model seems, not really very, Einstein is a theory, it's not a model. So let's start by looking at our own way of using language. And then maybe it will also be easier for us to better inform the public and the journalists, et cetera, et cetera. Just.
Okay, so one last question.
Hi, thank you for the wonderful talk. I have a question when you were mentioning about vacuum and the invisibles. So vacuum is the absence of what we know, like according to our knowledge. But as you mentioned, there can be invisible things which currently we do not know of. So those things could be interacting with a kind of force which is also unknown to us. So like you mentioned about the Higgs field, does vacuum have Higgs field, or it's the absence of it which we are not able to understand? Or
Excellent. You're absolutely right. The vacuum does contain the Higgs field, but that's what we know. By now we know it because, as I said, we made this experiment in which we started beating on the vacuum and all of a sudden waves popped up. So we do know that. We do know that as a fact. On the other hand, the vacuum might contain more. There could be one of the things that DP was, fascinated by was the fact that there is not a single Higgs, but there are many Higgses. And if there are many Higgses, there are other objects, other Higgs fields that in principle may have this density in the vacuum. So the vacuum could be populated not only by our Higgs, the one we know, but also by others. As you probably heard, the universe is expanding. The expansion of the universe, the accelerated expansion, everybody knows it's expanding, but it's expanding and accelerating. So the acceleration of the expansion of the universe is driven by some form of energy, which is not the Higgs, it's something else. So clearly there has to be something else in the vacuum that leads to the acceleration of the universe. So indeed, the vacuum is, everything that will end up being in the equivalent of a standard model at the end of everything. So when we will have a full picture, everything we add to, let's call it the Lagrangian, if you know what it is, of nature, will have potentially a contribution to the vacuum. The vacuum is a very rich object. There is, of course, we can pull out, I talked about quark, anti-quarks, coming up. We always say we pull it out from the vacuum because we put energy in the vacuum, but that is a local phenomenon. Something like the Higgs is not local. The Higgs is everywhere in the universe. And other things could be there as well, and most likely are there as well.
Okay, so we have one final question from YouTube. So Shubham.
Yeah, it goes as, is it known if neutrino is supposed to interact with dark matter since it travels very long distances?
No, it's not known. Certainly, there is no experimental evidence. We can certainly put limits on how strongly it might interact with that. The point is that if a neutrino interacts with dark matter and then it scatters away, there is no, using a force which is in this hidden sector, there is no evidence of that even having happened. So in that sense, we have no, unless it's a catastrophic event, but it cannot be catastrophic because otherwise there would be strong forces involved, right? Dark matter can interact through weak interactions. That's one of the assumptions, meaning the W, etc. And neutrinos interact with the W. So certainly there can be, if you know what I'm saying, a neutral current exchange of a Z between dark matter and the neutrino, but it's very small and it doesn't have visible consequences.
Okay, with that, let's thank Michelangelo again for this wonderful talk.